Okay, hi everybody. Thank you for joining. Today we're going to be going through the TechNote 205 on covalent coupling by Bangs Laboratories Inc. This was just a really good resource for me in my graduate research working on developing immunoassays for pathogen detection. However, in general, it's just a really interesting way to learn about one, how immunoassays work whenever you're using a labeling technique by attaching, for example, fluorescent nanoparticles to an antibody. But this is also the technique that you use to permanently bound biomolecules together. And so it's kind of like, the hardware of chemistry. It's so interesting. And personally, I don't come from the strongest chemistry background. And so learning this in a laboratory hands-on was a really magical way of going about it. You really realize that, the micro world is crazy and we can't see it unless you've got, one of those really sweet microscopes. But if you use these methods and these protocols, then you can still be changing what's happening down there in the tiny world. I think it's really cool. Anyways, so this is just going to go through TechNote 205. First of all, this is part of a series, so they also discuss, so this is one of the first ones you maybe want to take a look at. Plenty of time. I just gotta, I'm on the free Zoom right now. So TechNote 201, definitely worth checking out. I actually haven't looked at the other two they're suggesting, 204 and 101. But honestly, after making this video, I might take a peek. Like, this stuff is cool. So yeah, it's very all-inclusive. It goes through the different steps in designing a binding protocol and then also for optimizing it. Additionally, it gives you sample protocols. I'll show you which one I used myself. And this is great because if you're just starting out or if your lab doesn't already have an existing protocol, just straight up take something from one of these samples, do your research to figure out which one's best for your needs. And then after you've done it a few times and you've gotten the hang of the sort of results you're getting following their base protocol, then you can start incorporating exploring your options in order to optimize it to get better results. It depends on what you're doing it for. They've also got some miscellaneous coupling strategies. It's interesting. I never used that stuff too much. Yeah, the crux of it though is this first part on the design and optimization. It's cool to learn about the different aspects, and then the sampling protocols are just perfect. Okay, so let's go through this section, binding protocol and design optimization. Here we go. So essentially what you're working with when you're making these protocols is, what are you trying to bind together? In my case, in my lab, what we were doing is getting fluorescent nanoparticles, so those were the microsphere, and we were trying to permanently attach them to antibodies. And that's then how we detected antigens. You might be doing something different, but it's still going to be, what microsphere are you working with? And then what biomolecule are you working with? So 1, reactive groups and coupling chemistries, ligand. As activity and binding kinetics are highly dependent upon orientation of the immobilized molecule, reactive groups that are available for coupling or modification should be carefully considered. The ligand in this case would be the antibody. In this case, antibodies can bind to things through their amine groups. So I know that I'm looking for a protocol that can bind to amine groups. So 2, microsphere. Once you know what ligand you're working with, you need to choose your microsphere. Biomolecules may be coupled to polymeric or silica microspheres through a variety of surface chemistries. This is what sort of functional groups the microsphere has on its surface. These functional groups that are available include polymeric, carboxyl, and amino, most readily available, as well as hydroxyl, hydrazide, and chloromethyl, silica, silanol, carboxyl. Definitely, this is the area you should be spending the most time on researching. Depending on the functional groups you need, the answer might be obvious. Definitely, I've always really just heard of people doing carboxyl and amino for the polymeric microspheres. But maybe you've got a cool project happening. Maybe you have something that needs a little added funkiness. And then 3, the cross-linking reagent. So if I were to just straight up put my microsphere in a bath with the antibodies, yeah, sure, chemistry loves to happen, but it doesn't love to stay. So maybe you would get some action there if everything worked out, but it's not going to be permanently bound together, which is the whole goal here. You want those things locked together. So that's where a cross-linking reagent, also called linkers, spacers, activated. There are a number of chemical compounds that may be employed to modify or bind to the available reactive group on the bead or biomolecule. Cross-linking reagents may be used to activate groups that exhibit low reactivity in an aqueous environment. It gives the example of carbodiamide, correct me, for binding to carboxyl groups or to join groups that are simply not reactive towards one another, amine to amine. Certain types of linkers function as spacers, extending the biomolecule from the solid surface, often used in the coupling of small molecules or oligonucleotides to address steric effects. This is huge. The microspheres that you're working with are typically much larger than the ligand you're attaching to. But if it isn't, and you need to just have physical space, so there's room there for stuff to happen, then you got to have a spacer. And then linkers can also simplify conjugations or confer cleavability. So those are your reactive groups. That's step 1. Step 2, microsphere composition. The specific composition of the microsphere is going to determine the characteristics such as hydrophobicity, hydrophilicity, positive or negative charge, surface charge density, etc. These characteristics will have some influence on the loading capacity. For example, how efficiently the biomolecule will come into proximity of the chemical group so that coupling may occur. They will also affect nonspecific binding characteristics, although nonspecific binding may be addressed with blockers, buffers, test assay conditions, for example, sample dilution, etc. Right, this is really interesting. I'll give it another, all my examples can just come from my research. That's all I can do. I would love to just play with this stuff and do a bunch of different experiments for the different requirements. That would be cool. So in my assays, we are using wax printed microfluidic chips. So hydrophobicity, hydrophilicity is really important in my tests. I really need the molecules to, be relatively hydrophilic. They need to be able to flow in water and not just attach to my hydrophobic barriers, creating the microfluidic channel. Now, I will tell you, our molecules that was one of the main issues we ran into, is that just with the composition of the microsphere, you can get a lot of aggregation and clumping of the microspheres on the hydrophobic walls. And that was just something that we had to take into account. But as much as we could, we were choosing the hydrophilic route to help it flow. Positive and negative charge, this is also really important. Basically, I am just a huge fan of know the fundamentals of your experiment. What has a positive charge? What has a negative charge? What's relatively non-polar? What's the surface charge? All of this stuff is so cool. But yeah, so that's something you're going to want to think about. Next, reagent quality. This is when you're just thinking about the manufacturers. I'm not going to read this because I don't think it's as interesting. But definitely when you're purchasing your materials, look at the specs they give you. Oftentimes, something that they don't tell you about is the they can't manufacturers. Ignorant me thought that it should be really easy for them to tell me how many antibodies would bind to the surface of the microsphere. However, that just seemed to be a very hard piece of data to get, the number of parking spots on the microsphere. And so sometimes that's something that I would need to ask them via email before actually purchasing the molecules, excuse me. Okay, I also see that I have less than a minute left in my free Zoom. So maybe I'll have to continue this later. Next up, we'll be going through cool stuff. These are some really good equations just to keep in mind, and they relate to that parking sphere stuff. So, okay, thank you.